Our last section that we're going to cover on functions in this chapter is inverse functions. Okay, so let's take a look at this. Before we define an inverse function, we need to define one-to-one. So I'm going to remind you first of all, what does it mean to even have a function? So recall that a function is any rule, however we make up that rule, that sends inputs to outputs in a way that every input has exactly one output. Okay? So y equals f of x if there's one y for every x. And we've talked about when we did this exact example in a previous section where we defined functions, your function does not have to be what we call one-to-one. You can have multiple x values with the same y value. It's just every x has to have one y. So I had an example of a function where 1 has one output, 2 has one output, 3 has one output, and the outputs are all different. And then I had an example of one that was not a function because 2 has too many outputs. 2 is going to 4 and 5, that's too many outputs. And then I had this third example that I said sometimes confuses people a little bit at first, or they might think this is not going to be a function because of the two arrows going to 4. But 1's going to 4, that's one output. 2's going to 4, that's one output. 3's going to 6, that's one output. It satisfies the definition of a function. The property that my first example here has and the third one doesn't is that the first one's one-to-one. All of my y values, 4, 5, and 6, are different. But if 1 and 2 are both going to 4, that function is not one-to-one. The reason we're talking about this is we're going to try to define the inverse function, which in terms of these arrow diagrams would just reverse the direction of the arrows. So if I took this function here that sends 1 to 6, 2 to 5, and 3 to 4, the inverse would send 6 to 1, 4 to 3, and 5 to 2. And that would be a function. If my function is not one-to-one and we reverse the arrows, we would have, like on this example, 4 going to 1 and 4 going to 2. It wouldn't be a function. So if we take a relation that's not one-to-one and we define its inverse, it would wind up not being a function. So when we define inverse functions, we want to start with one-to-one functions. And I will add, if a function is not one-to-one, sometimes we can restrict the domain and make it one-to-one. I'll talk about that more when I get to my last example with graphs. So here's the definition. So if the outputs are unique for each x, we get different y values for different x values, then our function's one-to-one. Or in other words, a function with domain A is called a one-to-one function if no two elements of our domain A have the same image, the same y values. So our y values, f of x1, would equal f of x2 if and only if x1 equals x2. If I had different x's, I would get different y's. I'm only going to get the same y's if I use the same x values, if my function's one-to-one. You can do a quick test of that if you have the graph using the horizontal line test. We talked about the vertical line test, which tells us how many y values we get for each x, and that tells us whether or not it's a function. If we look at horizontal lines, that'll tell us whether or not we're getting multiple x's with the same y values, whether or not it's going to be a one-to-one function. So a function's one-to-one if and only if all the horizontal lines hit exactly once. So the first picture there, we have a linear function which is one-to-one. All of my horizontal lines hit exactly once. I would say it passes the horizontal line test. It is a one-to-one function. The second picture is some quadratic function here where plus and minus values are hitting at the same points. We're getting two intersections for each of our horizontal lines. I have different x's that have the same y values, like 2 and negative 2 have the same y values, 1 and negative 1 have the same y values. So that fails the horizontal line test. The lines are hitting more than once. So that function is not one-to-one. They're both functions that pass the vertical line test, but the one on the left is one-to-one, the one on the right is not one-to-one. And the reason we define one-to-one again is because it's embedded in our definition of an inverse function. So it says let f be a one-to-one function. So we're going to start with a one-to-one function that has domain A and range B. So we got inputs going from A to outputs in B. Then the inverse function, and our notation is to use a power of -1, and we have to be careful with that. That's kind of the universal notation in math for inverses. You might be used to working with inverses of numbers, which are reciprocals. That is not the case for the function. F to the -1 is not 1 over f. It's the inverse function. Okay? It's the one that does exactly the opposite. It swaps the domain and range. It has domain B and range A. And f inverse of y equals x if and only if f of x equals y. Or in other words, if you have the point xy for your function f, then the point yx would be a point for your function f inverse. Okay, they undo each other. So I have the little picture. If you start at x and you apply f, you get over here to y. If you apply f inverse, it sends you right back to x. So that's what an inverse function is. Let's look at one more quick example. This is a short example, again, just to kind of emphasize the definition. So if f of 2 equals 10 and f of negative 3 equals 7, then what are f inverse of 10 and f inverse of 7? Okay? So I've set up the arrow diagrams here. We only know the two values. We know that my function f sends 2 to 10 and negative 3 to 7. So f of 2 is 10. Well, the inverse just changes the direction of that arrow. Okay? If f of 2 is 10, f inverse of 10 is 2. Okay? That's the definition of the inverse there. If f of negative 3 is 7, the inverse, we're going to change the direction of the arrow there. F inverse of 7 is negative 3. Okay? So there it is in terms of arrows. You could also think in terms of ordered pairs. If we listed these as ordered pairs, f has the points 2, 10, and negative 3, 7. F inverse, you're going to swap your x and y coordinates around, and it has the point 10, 2, and 7, negative 3. Okay? So f inverse of 10 would be 2, f inverse of 7 would be negative 3. It's just showing you the definition of the inverse.